You ask an AI agent to execute a complex engineering task. It begins processing, encounters a requirement requiring highly specific localized knowledge, and abruptly halts. The base model lacks the context of your specific environment. To bridge the gap between a base model's general intelligence and a team's highly specific workflow preferences, we use skills. These are essential extension points that plug directly into the agent. This diagram illustrates the professional trap. Developers try to build these skills by writing massive, monolithic text prompts. The single document block expands rapidly until it hits the boundaries of the context window, saturating the agent's memory and crashing the process. Fixing this requires abandoning text prompts entirely. Instead, developers must architect extensible software modules. This modular approach relies on a strict three-stage engineering pipeline: architecture, instruction design, and evaluation. Treating agent skills as a structured engineering pipeline allows you to scale AI capabilities upward without degrading the base model's performance and memory capacity. The first phase of this pipeline establishes the physical architecture and the trigger mechanisms. An agent skill branches from a root folder into a skill.md file and optional folders for scripts, references, and assets. Skill.md splits into the front matter trigger and the instruction body. Auxiliary folders separate the logic: code in scripts, documentation in references, templates in assets. This architecture serves two categories of skills. Capability skills bridge temporary gaps in the base model, like PDF form filling. Preference skills are durable components that encode your team's specific code review workflows. Dumping all this logic into a single file instantly bloats the context window. Separating it into distinct folders enables context-lazy loading. This shows sequential loading. Skill.md front matter is always loaded. The body loads after the trigger fires. Reference files load strictly on demand. If a reference document exceeds 500 lines, it requires a table of contents with line hints, ensuring efficient navigation without scanning unnecessary text. The front matter description operates as the trigger mechanism for this entire layered architecture. This layout compares a vague trigger with an actionable one. A description like API helper leaves the agent guessing. The correct approach clearly defines the what and the when, specifying its use for text generation or multi-turn chat via the Gemini API. By structuring a skill as a lazy loaded file system with precise triggers, the agent holds only the exact instructions it needs at any given millisecond. This drastically reduces context bloat. With the architecture established, Phase 2 addresses instruction engineering, specifically the markdown written in the body of the skill.md file. Agents require gap-filling directives. Providing them with comprehensive essays or trivial context slows down their processing and degrades their performance. Leading with a brief 5-line code snippet is highly effective. When you do establish a rule, explain the why behind it. This teaches the model to generalize beyond specific memorized test cases. The procedural trap happens when developers dictate rigid, step-by-step instructions. If the path breaks, the sequence fails. Dictating exact sequences removes adaptability. The solution is declarative framing.
By stating the end goal, the agent dynamically navigates around obstacles to reach the target. Instead of a procedural command detailing how to find a text string, use a declarative goal. Update the database port to the user's specified value. Developers must provide constraints. Set strict boundaries like always run tests before opening a pull request. There is a hard engineering rule here. If exact sequential execution is truly mandatory for a task to complete, you should write a traditional script, not an LLM skill. It is equally critical to define negative cases. You must explicitly state when a skill should not fire. A broad description like use for any coding task causes request hijacking. The skill will constantly override base logic, even on completely unrelated tasks. Using declarative constraints rather than procedural steps leverages the LLM's natural reasoning capabilities. This creates resilient workflows that recover from edge cases where traditional logic would simply crash. The final phase of the pipeline ensures these modules function safely at scale: evaluation and lifecycle management. Because agent outputs are non-deterministic, a single pass-fail unit test provides zero statistical value.
This graph maps an evaluation framework. You need 10 to 20 distinct prompts covering positive triggers, negative constraints, and edge cases. Execute 3 to 5 separate trials per prompt. Over multiple runs, a distribution pattern emerges, revealing the true variance of the model's behavior. When grading these trials, evaluate the final outcome. Confirm whether the code compiles or the proper API is called, rather than restricting the specific reasoning path the agent took. Each trial must be isolated in a clean testing environment. Allowing context to bleed between runs masks real failures. Once a skill enters production, it begins a lifecycle. Capability skills, in particular, have a natural shelf life. As organizations deploy newer, more advanced base models, the specific logic gaps those skills were built to patch will close. You handle this with a deprecation test. Periodically run evaluations without the skill active. If the base model passes the test natively, retire the skill. Evaluating statistically prevents brittle overfitting. It guarantees the skill is robust across thousands of unpredictable invocations and provides a clear metric for sunsetting the logic when it is no longer needed. This full system flow represents the structural transition from monolithic prompt writing to a rigorous pipeline. Modular folder architecture feeding into declarative constraints and filtering through statistical evaluation. Mastering architecture, declarative instructions, and statistical evaluation maximizes agent adaptability across complex tasks. Building agent extensions is not about hacking prompts. It is about architecting resilient software systems that harness non-deterministic intelligence safely. Expand your practical, hands-on application of these methodologies by visiting the Learn by Doing with Steven YouTube channel. And to explore the deeper theoretical frameworks behind agentic workflows, check out the Steven Data Talk podcast, available on YouTube Music, Spotify, and major podcast platforms. The difference between a fragile AI experiment and a production-grade enterprise agent lies entirely in the engineering discipline applied to its skills.